I'm actually Sherman Chow. I'm speaking on behalf of my student and Jet and my colleague Hoover. Here we are talking about ECDSA, which stands for Elliptic Curve Digital Signature Algorithm. So that is widely used in blockchain application, in particular cryptocurrency. And when cryptocurrency is involved, the stake is high. So namely, if the private key behind the ECDSA algorithm is compromised, it will lead to great financial loss. So to avoid this kind of single port failure issue, we may want to apply a TN threshold signing or particularly TN threshold ECDSA. The idea is that we will share the private key to n parties such that anyone who managed to compromise T-1 parties cannot issue a signature, but any T out of this n party can do so. So because any T out of those parties can do so, we can ensure high availability, which is suitable for decentralized applications such as cryptocurrency and also DNSSEC. Unfortunately, we noticed that all existing threshold ECDSA scheme actually suffer from this kind of denial of service vulnerability. Namely, if an adversary can induce any sort of error in the process, or sider which want to complete the protocol need to restart from scratch. So with that, then let's talk about what can be the possible defense we are hoping for. So the baseline is we want to identify the source of the fault, which the literature call it identifiable abort or IA in short. So this even works in the case of dishonest majority. And if we manage to have honest majority remain, we can do something better, which is the literature called robustless. We can actually continue the protocol without possibly restarting from scratch. So ideally, we may want to achieve both when we have the appropriate number of honest parties remain. So we want to achieve both identifiable abort and robustless. Namely, we can both identify the error source, and in case we still have more than T honest party involved, we can continue the protocol. And you may think that DOS vulnerability may not be that serious, but on the other hand, because we are talking about decentralized applications, so this kind of error may be easier to induce. And in time-critical application, buying time can lead to some big consequence. For example, in a DAO application, decision-making process is delayed, or in DNSSEC, it can be having some kind of DNS poisoning work going on if the signature is not issued on time. So with that, let's take a look at the state of the art. There are actually many excellent ECDSA or threshold ECDSA scheme proposed, but only a handful of them try to take care of this kind of situation. So like all this work you can see on the screen actually can achieve IA. And notably, there's only one recent scheme from 2020. They achieve some form of self-healing. Namely, if the pre-computation phase is done perfectly, pre-computation phase is when the message is still not yet known, the party can try to prepare something ahead. We also call it pre-signature. So in case that part has been taken care of nicely, no one abort, then we can have online self-healing. But in case there are some error in the online process, one such pre-signature will also be used. So that is not a satisfactory situation. So with that, then that is the goal of our work. We want to achieve self-healing threshold ECDSA without restarting. And of course, we need to pay some price, but we also want to keep the overhead minimal. You may notice that we actually need to have one more run more than the state of the art. So that extra one arguably is for the so-called tier out of n flexibility. And we may also need two more runs in case we need to resolve the error. So we use scarce group-based encryption, which in particular avoid the verifier specific range proof in the pair-based construction, which is of order n square size. But that said, that is not our only change. We still need to ensure other kind of verification material is also at most of order n size, where n is a signed party. So there's still one part on the screen which I did not explain. So for here, n pi stands for the number of participants. So for easier discussion, I will just call it n throughout the talk, although you will see n prime on the slides. So the idea is that for all this scheme, they need to fix the so-called symmetry set or the silent set. Namely, because we want to protect the TN share the private key, so that's natural for the ECDSA process to introduce some randomness, right? So in the offline pre-computation, they will generate distributed randomness, but all those existing schemes that you have seen in the previous slide actually runs in the following manner. So the parties will join a silent set S of size n. Then after this process, the silent process basically degenerate to the n of n long threshold silent. So we will proceed with they will proceed with generating n of n randomness, but those p-signature generated will only work for the exact same set for the later online silent process. So it is not that flexible, that's not really threshold. So as an illustration, so for example, we have 5 persons here, all 5 of them, once they joined it, they must stay online and remain honest forever, such that the signature will eventually be issued. Otherwise, you need to restart from scratch. So now comes to the technical part of the talk. So on the left-hand side of the screen, you'll see basically ECDSA. There are many variables, but of those particular interest is the randomness K and the secret key S, which eventually we need to compute something called pseudo key K times S, which will be used in the signature. And then in the first whole ECDSA, ideally, we want to generate everything in share. So secret share of K, secret share of KS, which we use 5 to denote that. And K will be in Sharmy secret sharing. So you'll see Lagrange interpolation, Lagrange coefficient here. And also S will also be shared in the same manner. So you see the same Lagrange coefficient. Notice that this Lagrange coefficient is actually set dependent. So looking ahead, that is one of the reasons why the silent set will be fixed. So now let us focus on this part. So that will be the template of the first whole ECDSA. So eventually we want to generate ECDSA signature in this format. We have KM and RKS. So by the linearity, we can generate the TN share of both terms. And the first term, M is actually the message to sign. We can easily secret share that because that's publicly known. Everybody knows about that. So the more complicated case, which also covers the simpler case, is KS. And R for here is just a hash of a long value. So that's a publicly known constant. So now we focus on how do we deal with these KS terms where K and S are both first or secret shared. So to warm up, let's talk about how existing work approach this problem. So we have NN case. Let's use two cases as an example. So we have K equal to K1 plus K2, S equal to S1 plus S2. So those party 1 contribution will be in red, 2 will be in blue. So for computing the term KS, to write it out, we have all these cross terms. So for example, if we focus on K1, S2, we cannot just review it, because if you review it to say party 1, then S2, which is the secret key for secret key share of party 2, can be easily reviewed, which is not good at all. So to fix it, we use the MTA protocol. MTA stands for multiplicative to additive share conversion. So the idea is that we put K1 and S2 in this M2A protocol. They will generate alpha and beta such that alpha plus beta will equal to the result of K times S. So that is like we convert something multiplicative to an additive share. So now in the few slides ahead, you will see a lot of K and S. Keep in mind that Ks is equal to alpha plus beta. So to complete the signature process, we need to reconstruct the share. So we basically sum up every share of KS. We have the original share from party 1, K and S1, and we have the share from MTA, those alpha and beta term. So we just add them together. The party 2 also do something similar. So according to what we have built up, so they can reconstruct KS, and then they can just reconstruct all these different KIS terms and eventually complete the signature. So that is a very rough overview of existing idea. So now let's talk about the more interesting case. So our goal is still the same, but we need to generate first whole TN share of KS. And now you can see Lagrange coefficient comes into the play. So that is our quick recall of the notation here. So we just assume we do the same or similar things. So party I with Ki and Si now compute Ki times Sj with party J via the MTA protocol. That's all good, but if we try to chiefly compute the share as in the NN case, it will fail because once we involve the Lagrange coefficient, we will fix the Salad set S, which is what we want to avoid, because chances are there can be one people who just abort for whatever reason, then the material prepared here will be useless. So now the idea to maintain the TN threshold throughout the silent process is that we have the following crucial observation. We observe these two terms eventually in the reconstruction equation will share the same Lagrange coefficient. So with that in mind, we can actually proceed with the reconstruction, but with the multiplication of the Lagrange term deferred. So basically, it goes like what we have seen before. So party I will this term, party J will another term. When they combine them together, they will get back the desired result in terms of Ki times Sj plus Kj plus Si, those cost terms useful to eventually reconstruct Ks. But we still have a problem. It is okay for one invocation, but if we try to run it twice, then we run into the problem of having two equations, two unknown, because Si and Sj will be fixed, K will be varying. So in a nutshell, it is not okay to just directly reviewing this term. So that comes to our final fix in terms of security. So the idea is that we add in secret sharing of 0 on spot. So notice that because we just try to generate those secret share on spot, so the share here doesn't really matter. It is unlike the term we need to deal with because it's not related to any static sequence here at all or the silent randomness Ki at all. So with that, then we can reconstruct the Fe terms and eventually Ks, which is our ultimate goal. But that is all based on one crucial fact that Fe share is correct. So now it comes to the final ingredient I would like to share today is about the checking step to ensure the correctness. So time is limited, so let me quickly give you some idea. So the idea is that if we just deal with the secret share, things are unstructured, and so the ingredient or the upgrade we use is we use a variant called MTA with check, which will output a biproduct of G beta. Beta is those alpha and beta we mentioned before. And then we try to reconstruct the secret S in the exponent. With that, then also through the use of zero knowledge proof, and with respect to the S, which is the public key, which is publicly known, then we can do that with order n proof. So in particular, if you just expect Fe turns out, that will be something once into the situation of like order n square proof because you need to prove Fe terms with respect to Fe pair of parties. Okay, so I will end the technical discussion here. So apparently I will talk about other things, for example, like key generation. By the way, you have already heard something about PSS from PS talks, so hence I omitted it here. So now let me quickly share with you some of the performance results. So here is our setting. We try to compare with the state of the art, eventually published in Theoretical Computer Science Journal in this year. So they consider n out of n setting. So our focus here is try to compare each party's total incoming communication when we have cheater and what happened when we need to remove the cheater. And in particular, we focus on two possible steps within the offline signature preparation, which things can go on, which is the MTA process and the share review process, which is just before the pre-signature reconstruction. So here is the first of two slides about the evaluation results. So if low error occur, we actually need to spend more communication than the existing scheme. So as you can see, there is quite like 40% more than that. It actually stems from our identification material ensuring the recovery. So that is like the price. But in case we do have some error, then you will notice that we just add a little bit of overhead. Versus in existing scheme, you need to have a more costly procedure to report the misbehavior, and you also need to restart the whole protocol from scratch. And in this case, we will have some significant saving. So that is about communication cost, and we also talk about one time. So in a nutshell, we also have some saving in one time in case we need to do the recovery, and more detail can be found in the paper. So with that, I would like to conclude this talk. So our virtual ECDSA is tricky to implement because of its nonlinear structure. So most existing schemes chose to degenerate it to a n out of n non-virtual silent. And so with that, then any fault, either there's a benign mistake or an intended error, it will require restarting from scratch. It will basically affect the performance claim in communication cost or communication one, because we need to restart things from scratch. So for this work, our aim is to achieve virtual silence for real throughout all phases, namely key generation, offline, online silence. And with that, that is sort of a new idea, or at least a new direction. So a lateral question we ask ourselves is, can we achieve something even better? So with that, I would like to conclude my talk. And in case you have further questions, I can be contacted at this email address. Thank you so much.
Sharman, let me ask you one question, or well, a couple of them. One, why do you use CCL as a benchmark? And second, on your performance results on execution time, what was the platform that you use for those results?
Sure. So thanks for raising this question. So I should make myself a little bit clearer. So as you can see on the screen, there are many schemes particularly pay attention to dishonest majority or any kind of recovery. So in that case, a lateral question would be, why don't we compare with this one? But on the other hand, the idea is that now we run into this situation, so that is either lesser one, but we have order n square of communication. For this one, it is the same number of run, same order of magnitude for the verification cost, and hence in this case, this is actually better than the previous scheme, and hence we only focus on comparing with this newer scheme. So that is my answer to your question one. And for question two, basically we just run it in a regular desktop platform that is like some simple AMD machine my student have in the student lab. And actually, as you might see, the focus is about communication, so the platform doesn't matter much, but yes, the runtime matter. But yeah, we just use a regular desktop.